turbulence, and this will go on probably for another 2 or 3 classes, where we will, as we discussed, we will talk about some qualitative aspects of turbulence first, and there will be some quantitative analysis introduced, but to you, lot of it may look like hand waving to you, and often it is hand waving, but it's done with keeping the physics in mind. So the hand waving is not as crude or as arbitrary as it appears. Okay. So we will be doing this, and what we will find is that using such arguments, we are able to come up with some very nice estimates which are of importance to us even as far as computations go, but we will not probably be looking at any equation as such to get these points home. That is what we are going to do. So we talked about some features of turbulence. Now, among the mathematical tools which will be used to study turbulence, the first tool which we will use, and which may look very sort of outrageous or very simplistic, will be the dimensional analysis. And we will get relations between variables. Dimensional analysis helps us to get relations between variables in terms of an unknown dimensionless constant or some sort of a dimensionless function. That is what we are able to achieve with dimensional analysis, and we will soon see that maybe in the next lecture or lecture after that, how we use dimensional analysis. In fact, there are two theories by Kolmogorov. Kolmogorov was a Russian mathematician. In probability theory, Kolmogorov is very well known, and Kolmogorov in 1941 wrote 2 papers, and in both of those we will see extensive use of, we will do the crux of those papers, we will not follow his whole paper, but we will show how dimensional analysis is used to come to some estimates. So sometimes this Kolmogorov's 1941 is referred to as K41A and K41B, the 2 papers of his where we use some of these arguments. The second tool, of course, which we will use, and we have already talked about this, will be statistical analysis. Yeah, come in. लेट पाओ तो सीधे घुसाया करो, पूछा मत करो. We'll talk of quantities like mean, variance and their properties, and related to these many more terms will come: homogeneity, statistically stationary flow and things like that. So statistical analysis becomes an important part of when we try to develop a theory of turbulence. And then another technique or another tool which we use is called asymptotic invariance. And as we have seen, turbulence is a high Reynolds number phenomena. So any proper description should behave properly as Reynolds number becomes very large, and which we write by saying as Reynolds number tends to infinity. And this will provide very powerful constraints. And this asymptotic invariance, we will find this is related to small effects of viscosity at high Reynolds number. I am using RE for Reynolds number. So, at high Reynolds number, and see this infinity type of an argument, actually I do not know if you, how many of you have heard of Stokes paradox, or Stokes was not the, so there was Stokes was 3D and 2D, D'Alembert's paradox, not Stokes, I stand corrected, D'Alembert's paradox. D'Alembert's paradox was something which is related to behavior at infinite Reynolds number. Because what you find is that, and what D'Alembert's paradox essentially was, that drag force, when you look at the drag coefficient, then drag coefficient decreases, but at high Reynolds number it becomes constant. Now, what you expect is as Reynolds number goes to infinity, what happens to viscosity? Viscosity goes to 0. So, then it was expected that the drag should go to 0 when you reach infinite Reynolds number. Obviously, we do not reach infinite, we are somewhere less. So, what we expected was that as Reynolds number goes to very, very high limits, at least the drag should reduce, but drag did not reduce, it goes up. CD becomes constant means drag goes up like V square. So, drag did not reduce, and this is what was referred to as D'Alembert's paradox, and the resolution of that, because at infinity you expect this to go to 0, but it did not go to 0, and the resolution came from the boundary layer theory. Okay. So, these sort of, so that is what is an example of an asymptotic invariance, that as things go in the limit, either something going to 0 or infinity, then you would expect some sort of a behavior. And can we predict that? That is what we are doing in asymptotic invariance. So, now let us try to, so now having seen some of this, but next what we will see is what is, can we get some estimates of diffusivity in a turbulent flow. Now, what do we mean by diffusivity? Diffusivity is the property by which things get smeared in a flow. If it is heat transfer equation, then the way temperature gets distributed in the flow. When we talk of this equation, when we talk of fluid mechanics or we talk of momentum, then the way the momentum is dispersed in the fluid. And as we have discussed, one of the qualities we find is that turbulent flow mixing is much more efficient. So, what would you expect should happen to diffusivity in a turbulent flow? Should it be lower than laminar flow? So, diffusivity is that coefficient which we use, which I will just introduce. Should it be lower or higher in a turbulent flow? Obviously, much higher. And in fact, keeping that in mind, the next topic will come, well, let me complete this today, but where we talk of in turbulent flows, we introduce an artificial viscosity or an artificial diffusivity. And does anyone know the name of that? In some of the models, we call it eddy diffusivity, eddy viscosity, or eddy. In general, if I use diffusivity as a term, so eddy viscosity. So, now let us try to get some estimates of diffusivity in a turbulent flow. and I am taking two simple examples first. And these simple examples will be, which are there to just introduce these methods. Because in the first example, what one assumes is that we are looking at diffusion in a problem with imposed length scale. So that means physics of the problem tells us that there is some length scale. Okay? It doesn't give us any time scale automatically. We will be able to deduce, and also there is a length scale, there is no per se velocity scale in the problem, which we will probably have to work out. And to make life simpler, let me look at the diffusion of temperature. Thermal diffusivity is what I am going to address. So, let us look at a problem where one has a room of dimension L. So, now let us say we are talking of this room, let us assume it is cubical, it is a cuboidal in shape. So, that means each dimension is L of the room. Of course, I do not want to introduce multiple scales here, but even if 2L is there, then the order still stays as L. So, here if I am talking of this room, L will be the height or the width, which is almost equal, and this is about double of that, so that also suffices. Okay. So, and in this room, we install a heater. So, we just keep a heater, there is no movement, nobody is there in the room, we are not moving. So, there is no velocity being caused by movement of anything else, just the heater has been put. Okay. So, there is no air motion and heat is dissipated by molecular diffusion. Let theta be the temperature, and let gamma be the thermal diffusivity, and I presume you may have seen some heat transfer equation. I will write the equation also, but gamma is something like K over rho C. K is the thermal conductivity and rho C. So, now if you look at the equation for temperature, because there is no convection, it is partial theta by partial T is equal to gamma times this is the standard equation of heat conduction. You may have seen it, even if you have not, this gamma you may have seen it as, you may have seen this equation as m rho C d partial theta by partial T is equal to K times del square T. That is the same equation. Okay? And if you, so this is the general equation of heat transfer. I initially said I will not have any equations, but I have introduced one, but I will not be solving the equation. That is what I meant when I said there will be no equation. Now, what we are doing, and this is what I want you to appreciate, we are looking for a general order of magnitude, and let Tm be the molecular time scale. When there is only conduction, I say the time scale, the diffusion is taking place only because of molecular diffusivity or molecular conduction. So, I say this time scale is T sub m. So, here now what I am writing is an order of magnitude equation. Delta theta upon Tm is of the order of gamma times delta theta upon L square. First, just let's have a look at this equation. Obviously, where does this come from? From the equation. But it doesn't come from solving the equation. We are just doing an order of magnitude analysis. Now, partial theta by partial t, if you try to discretize it, all of you must have done some numerical course, is written as theta at t plus 1 minus theta at t divided by delta t. So, this theta between some time interval, again this is not an exact derivative I am calculating, is of the order of delta theta. The change in temperature which is taking place in the room. Let's say we start with temperature 10 degrees centigrade, so after some time it becomes 15, 16, whatever it is. So, delta theta represents that order of magnitude. It is not an exact number. And delta theta by delta t will be divided by t. This is the scale about which we want to find out the molecular time scale. And because there are two terms in the equation, both of them have to be of the same order. The second term is gamma is a constant, so that stays as gamma. Now, d2 theta by dxj, dxj, this is del square t. Del square t is what? d2t by dx square. Again, when you calculate it, will be delta theta divided by whatever is in the x side dimension square of that. So, I write it as delta theta upon L square. Is that fine? Yeah? This is molecular time scale, means time scale associated with this gamma when there is no turbulence. See, right now we are not assuming any turbulent flow, it's just conductivity which is taking place. So, you could think of molecular scale, time scale associated with just pure thermal conductivity. Okay? So, this, yeah?
Why is it that delta theta square?
No, because it's d2 theta. How do you expand del square t? T, have you done any finite difference? You must have done it somewhere. Del square t ko agar hum, if we expand it in a we write the discretized expression, what do you get? T at theta plus 1 minus 2 times t at theta xj plus 1 minus 2 times theta at xj plus theta at xj minus 1 divided by delta x square. So, each of the term on the top is of order delta theta. Okay? So, it won't be square. Had it been a t square somewhere, then it would become t square. See, the square is on d2, not on theta. Clear? Okay? So, this is what it is, and so based on this, what we get is this and again see, I am not using a equal to sign, because we are really, and in that sense I said the analysis is pretty crude. Doesn't involve any solution of any equation. But we are trying to use physics and trying to get to some of these numbers, just to get a feel of the orders. That's all we are doing here. So, Tm becomes equal to L square upon gamma. Okay? Now, gamma is a property of what? The air in the room. See, because heat is being dissipated in the air. So, now if I typically look at, let's say, a room where L is equal to 5 meters. Now, gamma for air, I just, under normal circumstances, is something like, I am not using SI units because the book where I have taken the example from did not use SI units, but obviously it will be otherwise 0.20 into 10 to the power of minus 4 meter square per second. So, based on this, what you get is Tm is of the order of 10 to the power of 6 seconds, which means 100 hours. So, to get some sort of an appreciable change by putting some sort of a heating element in the room, and we have not even said what is delta theta, how much change it is, but it will be of the order of many, many hours, of what, 4 days. if the heater keeps on working, and obviously this is assuming that there is no, and it also has to depend on the power of the heater, how much it is, if it is not too much, but that is what it is if there is no motion. But now,
Sir, we have not specified any delta theta, so how can we visualize how much change?
so this is just to find the time scale. Whatever delta theta is, that will get cancelled from both sides. But this is assuming that there is no motion at all. But actually what happens? Actually there is buoyancy. In a heater you don't, it doesn't, even in those vertical heaters we have where you still start feeling the heat after 1 or 2, after some time. The convector makes the room hotter much faster. But even those vertical heaters we have, after 1 or 2 hours we start feeling the heat. It is not that we don't feel the heat. But then why is that happening? Because there is some motion which is taking place because of the heaters working. This is assuming that there is no motion. Okay, so that is what would have happened. So this is also in some sense what I have calculated, this is a very theoretical time. In actual life this will not happen because buoyancy will be there. Air adjacent to the heater will get heated up, and that will cause some motion. So let us see what happens if we account for that motion. So for motion generated by buoyancy, let the turbulent motion, now what one finds, and this is again, now you have to take it on the face value, that once the motion becomes turbulent, then the large scale in a turbulent motion is, the largest scale is almost of the same size as the geometry which is confining the flow. That is the largest scale of the flow, because then the flow starts to move and then everything in the room starts to move. So we'll talk of this concept later. We have things like what we call as eddies, that air starts to move, it forms a vertical type of pattern, the hot air rises up, cool air comes down. So overall the largest scale of that motion will be something like L. Okay. Now let the characteristic velocity of this motion be u. Now physically this velocity, at least the way the problem was specified, has not been sort of discussed, but, and this is where now the delta theta is going to come up. And if the radiator which is generating the heat, if it heats air by delta theta, then the buoyant acceleration is equal to, now this term which I have written here, g is the acceleration due to gravity, delta theta is the change in temperature divided by the temperature in the room. And those of you who have seen the heat transfer equation in natural convection, this is the term which comes in on the right hand side as the acceleration term because of gravity, g delta theta. And if we non-dimensionalize everything by theta 0, then we get g delta theta by Grashof number. Probably there's something more in Grashof numbers, but it is related to the Grashof number. So g delta, and if you look at the dimensions again, so we have got the dimension of acceleration is g. So g delta theta by theta is the order of the acceleration of the fluid, where delta theta is the change in temperature. And that is where now the radiator's capacity comes into picture. If it is a stronger radiator, more wattage, delta theta will be more. Okay, because theta is the base temperature of the room. Okay, and if again we make some numbers, if delta theta is equal to 10K and theta is something like 300K or maybe slightly more, I am not so this g delta theta by theta, I think on 10 liya hai, 10 into 10 by 300, it's slightly, it's not exactly 300, I think but I'm just doing some, again, whether it is 0.3 or 0.25 or 0.35, it does not make a difference. Okay, so this acceleration turns out to be equal to 0.3 meters per second. And 0.03 होगी, जी 10 होगा, जी भी तो है. Okay, now if this eddy has a height, see what happens is, if there is no motion in the room, then eventually this delta theta dies down, and we feel the effect of delta theta only in a small range. After that you don't feel it, and this is a practical thing. You don't feel the effect of heater very far away from it. So if this eddy has a height of something like 0.1 meter, then the kinetic energy per unit mass of this eddy will be g times delta theta upon theta times h. And this again, if you look at the expression 2as, if s is the distance travelled, 2as is equal to Vf square minus Vi square. And again, looking at very simple type of explanation. So, and 2as, and if I divide it by 2, I get V square by 2, that gives me the kinetic energy per unit mass. So, that will be equal to the acceleration multiplied by the distance. So, if this effect is felt up till h, and therefore this term, therefore what we get is, we are trying to get the order of magnitude of this velocity, which we told as u, sorry. So, this is u square is equal to g delta theta upon theta times h. So, this will become now 0.03 meter square per second square. And so, the typical u here turns out to be equal to something of the order of 24 centimeters per second. Okay? This is just again square root of 0.06, and we work it out, and it's like this. But now we make another further this thing, that this is the velocity just above the heater. Now throughout the room the velocity will be very small. Okay, so an estimate, we say, we just do again hand waving argument, that throughout the room we take u as something like 5 centimeters per second. Now the length scale is 5 meters. So therefore the turbulent time scale, which I call as time turbulent, what will that be? The length scale is 5 meters, the velocity scale is 5 centimeters per second. So what will be the time scale? Again, very simple high school physics, L by U. So it will be just 100 divided by, it will be equal to L by U. So 5 divided by 0.05. So this will be equal to 100 seconds or it is of the order of 2 minutes. So while, and this is being, we are doing this to see that the diffusivity, molecular diffusivity, while the time scale of that is much bigger, but a typical motion like this causes a time scale of something much less. That means by any sort of motion, now whatever you could be, it could be from any, generated by anything, that makes the time scale go an order of magnitude less than what was the time scale due to diffusion alone. And this probably typically happens because diffusion constants are small. In SI units, when you look at it, they are something like 10 to the power of -5, -6. Nu when you look, and nu or K by rho C for air, all of these, it's 10 to the power of -5 in SI units. So they are small, therefore those time scales are much larger, but turbulent time scales or any this thing are much smaller. But then let's look at another thing. If we look at small eddies generated by the flow. Now, what I mean, and this we will do this, what we say is that there may, as I said, that if there is motion, there is one large eddy, but they keep on breaking into smaller and smaller eddies till you get to viscosity. And that theory will follow this chapter, which is what we call as the Kolmogorov's theory, where we, so now for this type of flow, and maybe I will ask you to calculate this as a homework or whatever for given this data, what we find is that the small eddies generated are of the order of 1 centimeter. The large eddy was 5 meters, but the small eddy which is there will be of the order of 1 centimeter, maybe even smaller. Okay. Now, what will be the rate or time scale of molecular diffusion of this small eddy? Now, the small eddy also will have some sort of molecular diffusion. So, what will be the rate of molecular diffusivity or time scale associated with this for the small eddy? And the time scale which we have seen earlier was capital L square by gamma. So, now here if this eddy has a scale of L, the time scale will be small L square by gamma, and if this is 1 centimeter square, so that means this will be equal to 1 centimeter square divided by 0.2 centimeter square per second, that was gamma, and this turns out to be equal to 5 seconds. So that means at the small scale, for the large eddy the molecular time scale is much larger, but diffusivity at a small scale is very fast. Even the molecular diffusivity, if the scales are small, is very fast. And this is what we will show as a correct property of turbulent flows. When things go to a very small scale, the diffusion, even the molecular diffusion, is not slow, it is fast. But overall, if we look at the turbulent time scale by the molecular time scale, the large one, so turbulent time scale was, what did we show? It was equal to L upon U into L square upon gamma. Molecular time scale was L square upon gamma, and for the large eddies the turbulent time scale was L upon U. So what does this give us? This gives us gamma upon UL. And let's say for air, Prandtl number is 0.73. Do we all know what is Prandtl number? Probably you will not know, but Prandtl number is a ratio of diffusivity of momentum to heat. So Prandtl number is 0.73, which means this Prandtl number is equal to nu upon gamma. In fact, probably alpha is what is used in your typical heat transfer course for diffusivity. Alpha is equal to K by rho C. Lumley's book used gamma, so I used gamma. This gamma is the same as what you will see as alpha in the heat transfer books. So again, this is of order 1. So since this is of order 1, what I can do is this time scale, in fact I should put it as again not equal to, and this will be of the order of the nu upon UL. And why do I do this? What is nu upon UL? 1 by Reynolds number. And for this example which we are doing, Reynolds number is something like 12,500 for these values of U and nu. So the reason why I am doing this is, this gives you a new physical meaning of Reynolds number for turbulent flows. Reynolds number can also be seen as a ratio of two time scales. If you are sleeping, you are a student of fluid mechanics, you have done 2 or 3 courses, you are sleeping, and I ask you what does the Reynolds number signify? What will you say? Inertia force to viscous force. ठीक है कि नहीं? अगर आप, if you have done any course and you have done 1 or 2 courses, it is drilled into your head. Reynolds number is inertia force to viscous force, and that is also right. But here what we understand from here is that the interpretation of Reynolds number is that Reynolds number can also be seen as a ratio of time scale with only molecular diffusivity, no motion present, to time scale with motion present or with turbulent motion present. Because any small motion, given the values of nu for air are so small, the motion tends to become turbulent. Yeah.
So, when we're talking about the convective current and this, the time scale with the motion present part.
Yeah.
So we took a U which was 5 centimeters per second or something.
Huh.
So, so are we assuming that all along the course of the convection, that block of air has a 5 centimeter per second velocity?
No, so that's why we reduced it. See, it was our initial estimate, if you see, what came out to be 25. So then what we said was that basically what this represents, the time scale here will represent, if you have an eddy, the time in which an eddy typically turns over. So the velocity is that velocity which is causing this. Okay. So this again, the 5 was again, it's all these numbers really just to give you a sense of the ratio of the numbers. So this whether it is 10,000 or 20,000 or 25,000 does not make a difference, but it is not 1. It is a big ratio or a small ratio depending on which is the numerator, which is the denominator. That is what we are trying to get to, that just with diffusion you get large time scales. But any motion is there, convective thing is there, whatever be its velocity. If it is 2, then you will get a slightly smaller number or slightly bigger number, whatever. But that makes a big difference in the time scale. That is what we are trying to show. So what we are, as I said, so here what we are trying to, what we have said is that Reynolds number can also be seen as a ratio of these two time scales. Because the reason why, let me also, this is what we typically say Reynolds number is, a ratio of inertia to viscous forces. Now, see, this comes maybe for your benefit. If we do in the Navier-Stokes equation, there's a viscous term, there's an inertial term. If we do order of magnitude of the inertial term, and if we do an order of magnitude of the viscous term and non-dimensionalize the equation, what we find is everything else, or the inertial terms have no coefficient, the viscous term has a coefficient 1 over r. So that's why Reynolds number denotes a ratio of inertia to viscous forces. But the reason why we would not like to use this thing in turbulent, this thing is that viscous forces, as we will discuss later, they act at very small length scales. In fact, this will be the whole notion behind Kolmogorov's theory, that as the eddies keep on breaking down, they keep on breaking till they reach a scale where they cannot break. And at that scale, they dissipate the energy into heat. So therefore, dissipation takes place at small length scales. Whereas the convective term, which leads to the inertia forces, they take place at large scales. So these two things are taking place at different scales in a turbulent flow. So the inertia forces, they are at large length scales. Okay? And therefore this explanation of Reynolds number being inertia to viscous forces, while is correct, but we are talking of two phenomena at two different scales. So it may not be a very good sort of a comparison to do. Now, what would you expect at a local level? Once I say that at the dissipation level, we go to the smallest eddy. What sort of a Reynolds number would you expect if I take the velocity scale of that eddy and the length scale of that small eddy? What sort of a Reynolds number will you expect there? Large or small? Small. And see, the eddies are breaking up because large Reynolds number means instability. So they keep on breaking, and they keep on breaking to a level where the local Reynolds number is almost of the order 1. So that these two forces are of the same area. And also, if you recall, we said inertia and viscous forces will interplay. So it all fits in the same picture. That is what we are saying here, and this is it. Okay. So now in the next class, again there is a new topic, so I will do it in the next class. I am going slow, but let it be like this. So initially 5-6 classes you may not find too much maths, you may find things like this, and for some problem you will be asked to maybe find the time scale and all. I'll give those to you to try out, but that's fine. In the next class we will introduce the concept of eddy diffusivity, and after that I am going to talk, so maybe if I finish this it's okay, and then I will talk of the Kolmogorov scale and the cascade theory, and after which we will move on to the equations. Okay.